Okay, picking up where we left off, let's see an example of this method in action. So we're going to use the same function that we had before, right? So we again want to approximate the integral from 1 to 2 of dx over x squared. Remember that that is 0.5 exactly. And we'll use m sub 5. So the midpoint rule with 5 subintervals. Then, again, our delta x is 0.2. This time we have to find the midpoints. So I can again write a table. So we have x sub i's, and we're going to need our x sub I bars, and then the function values at the x sub I bars, the midpoints. Okay, so we have 1, 1.2, 1.4, 1.6, 1.8, 2. I may have run out of room there prematurely, but whatever. So midpoint of 1 and 1.1, 1.2 is 1.1, 1.2 and 1.4 is 1.3, 1.4 and 1.6 is 1.5, and so on. You can see that they're the same distance apart. They're just like shifted by 0.1. And then we find the function values at those points. So 0.8264, 0.5917. You can use any calculator you have at your disposal. Just make sure that you're using consistent rounding off values. Okay, so this is where we're at. We have so far our the function values we need are on the bottom line. We found each midpoint using the initial data values. So rather than using the endpoints, which there would be 5 of, we're using 5 midpoints. Then m sub 5 is the sum from I equals 1 to 5 of the function values at the midpoints times delta x, which is just going to be add up all the function values, multiply by 0.2, and this is approximately equal to 0.4971. Not too bad. This yields the error, I got a little ahead of myself. But this yields the error I minus m sub 5, which is 0.5 minus this, and that's approximately 0.0029. That's already significant improvement. Okay, we're talking a full order of magnitude less than the error that we found using the left and right endpoint approximations. So it is a significant improvement. The question, though, is, as we're working through these sorts of techniques, how do we know that they're going to give us lower errors? So we use the same n number of subdivisions in both illustrations of the techniques. If we continue using larger and larger n's, but the same, do we see a similar pattern among the errors? So for that, we must talk about error bounds. So basically, we know as n goes to infinity, e of whatever technique we're working with, right? For instance here, e sub n, m of n, should also go to 0. right? We want that to be true. We hope that it's true. But how quickly? And how do we know what is like the maximum error we can get? So there's a lot of different factors here, obviously, right? So obviously n is a factor here. The function itself is a factor here. How wide our interval is a factor here. So here's what we can do. We have actually a theorem. Okay, so theorem that gives us an upper bound on the error that we can get from this procedure. So given if we know that the absolute value of f double prime of x is less than some capital K, some number, for all x in that interval a to b. So our second derivative of this function is bounded on this interval. Then we can guarantee that the absolute value of this error as a function of n is less than or equal to capital K times b minus a cubed all over 24n squared. Okay. There's a lot going on here, okay? But let's just focus on what this means, right? So some interpretation. First of all, K is constant, okay? K is this upper bound on the second derivative. So what we're saying is the error depends on the curvature or the concavity, how much the function curves. It also depends on the length of the interval that we're talking about. And lastly, it depends inversely with the square of n. So in other words, there is a relationship here between the number of subdivisions, the function itself, and the length of the interval over which we're integrating and the error. So two things to note here, okay? So important observations. One, and remember this depends on f itself, but this is for the bounds, right? We know that the limit as n goes to infinity of e sub m of n is going to be less than or equal to the limit as n goes to infinity of that bound, right? Over n squared. Oh, 24n squared, sorry. Of course, this whole thing is 0. So that means as n goes to infinity, the error goes to 0. Which is what we wanted, right? Perfect, great. 2, how quickly it goes to 0 is no more than 1 over n squared. So we would write this as e sub m is, I'm going to use what we call big O notation. This is, it looks weird, but I'm trying to do a big O. Yeah, let me draw it a little bit better, because you're going to see this notation later on. It's kind of a curly O. I'm trying to find an example of what it looks like when you're, well, I'll just write it like this. Is big O n squared. So it's dominated by n squared. If you write in a table, so for instance, depending on what n is, right? So you can go with one subinterval, which is just the interval itself, 10, 20, 50, 100. The error from this midpoint rule approximation is going to depend on, at most, a function of this squared in the denominator. So in other words, well, I wouldn't be able to write it here because we don't have a specific example, but it's saying that it depends on n squared in the denominator. So we'll talk about that in more detail later. But it also means that we can set some arbitrary tolerance epsilon and guarantee that the error is no bigger than that epsilon, as long as we find some minimum n that allows us to do that. Okay, and I'm not going to provide a proof of this result because we are not, unfortunately, we don't have the tools yet to really fully see a proof of this result, unfortunately. But theoretically, by the end of this course, you could.